Welcome back, everybody. We are once again continuing Chapter 3 on vectors, and in the last segment we had talked about the graphical mode of adding vectors together. While it's good for visualizing what vectors look like when added together, it is a little bit more error-prone, and it is certainly more time-consuming because you require a protractor and a ruler and stuff like that. So what I'm going to introduce to you today is the component method of vector addition, or subtraction for that matter. And this requires that we set up a table. It doesn't require a ruler or a protractor or anything, but we need to set up a table or a chart. And what we're going to be doing is breaking the vectors into their components and then adding them together to create the resultant vector that is the sum or the difference of the vectors that we're adding or subtracting. So I think it'll make more sense if we just go ahead and do it. So let's go ahead and example 3.5. Again, this will probably be, this will be number 3.5 for you. All right, so taking a walk around your backyard, you have three different vectors of motion that you take. All right, now these are not named, and this one right here, 5 paces due north, I'm going to just call vector A, very original, right? Vector B is going to be, I'll make that this purple one right here, vector B, and vector C, let's make that, use a different color, we'll use green, okay? And that is C, like so. And instead of paces, I don't like paces, that's not really a standard unit, we're just going to call them meters, all right? So 5 meters due north, 3 meters due east, and 4 meters at 45 degrees south of west. All right. We want to find the total displacement, d, using the component method. Now, it's not your total distance because you're going to be walking kind of all around in different directions right here. It's your total displacement. So it's really your displacement from the original origin to the place where they wind up adding up. So it's kind of like taking this and taking vector A and all right, vector A north, and then you get vector B, you're going east, like that. And again, don't do this because I'm actually going to erase it. And then vector C is going to be south of west, so it's going to be something kind of like that right there. And so vector D, we'll do that guy in blue, is going to be the sum of all those together. That's vector D. So it's your total displacement from the original origin to the end of where vector A, B, and C were added together. All right? So I'm going to erase that. And instead of drawing them graphically, we're going to actually add them together using the component method. So here's what I suggest that we do. I'm going to use probably the better part of this, this table right here to set up the graph. You may want to use maybe half of this area, or maybe 2/3 of this area. I'm going to use a good chunk of it to show you the graph. So I'm going to write V for vector. Okay? Here are V for vector. Mag for magnitude. Theta, you should know what theta is. That's our direction. And then I'm going to make 2 columns that are a little bit wider, actually. I'm going to write X, and underneath X, I'm going to put mag cosine theta. And under Y, I'm going to put mag sine theta, like so. All right, and I'm going to just kind of draw some dividers like this. Okay, so this is our table that we're setting up. And I'll explain why I wrote mag cosine theta and mag sine theta here in just a little bit. All right, but what we're going to be doing is this is going to be sort of our addition table, where we're going to add together vectors A, B, and C to get the resultant vector D. So let's go ahead and write down what we have for vector A. So this column right here is just the name of the vector, so we can keep them straight. All right, vector A, and then it'll be vector B and C down below it right there. Well, what's the magnitude of vector A? Well, vector A is going to be 5. We changed paces to meters, right? Let's just call that meters. So 5 meters, like so. Okay. What is the direction of vector A? Well, it says due north, all right, which is kind of like straight up like that. So how is that compared to the x-axis, well, that's a full 90 degrees off the x-axis, all right? So you can say this a couple different ways. You can say 90 degrees, oops, I didn't put my 0 after 9, 90 degrees north, or you can just put n for north, and what I oftentimes sometimes do is just put a little arrow that says it's going straight up like that, all right? And that kind of indicates the direction of this vector. And if you recall a second ago, that's the direction that I drew it in, all right? Now what's this whole x and then mag cosine theta, or y mag sine theta? Well, remember that if we go back, and in fact I will go back a couple slides to, where is it, right here, finding out how to find, here we are. Remember this? We found the scalar components. What those x and y columns are is they are the x component and the y component of that vector. And so we said before, to find the x component, we take the full vector, which is really the full magnitude. So this is the full magnitude of the vector, times a cosine of the angle theta to get the x. And then for the y component, we take the whole magnitude of the vector times the sine of that angle theta. And that's why I write mag cosine theta and mag sine theta at the top of our table right there, because that's just a reminder to me of what I need to do to get the x component and the y component. All right, so what is the magnitude of the full vector? Well, it's 5 meters, right? Times a cosine of theta. What's theta? Theta is 90 degrees. So if I go to my calculator and go 5 cosine 90, what do I get? Well, that's 0, because if you recall, cosine of 90 degrees is 0, so 0 times anything is 0. And if you think about it for a second, the question is, all right, this x component right here, what kind of x component does a completely vertical line have? It's got no x component because it's entirely vertical. It's not moving in the horizontal at all. So that makes sense. All right, what is mag sine theta? It is a magnitude of 5 times the sine of theta. Well, if you recall from math, the sine of 90 degrees is going to be 1. So 5 times the sine of 90 degrees, that's going to be 5, right? Because that vector, the magnitude of that vector, is entirely in the y direction. So it's going to be positive 5 meters in that direction right there. Okay, let's go ahead and do this for vector b. Get the main idea? Vector b is going to be, that's purple, right? All right. Vector b, that's the name of it. What's the magnitude? Magnitude is 3 paces, right? There's our 3 right there. So the magnitude is 3. Oh, we said we were going to do meters instead of paces, right? At what direction? Well, it's 0 degrees east, right? Entirely east, and I'll draw a little arrow to remind myself it's going completely east. It's no degrees north of east. Okay? You can write 0 degrees north of east if you want, but if you just think that if it's going all horizontal towards the east, it's 0 degrees due east. Okay, so what is the x component of that vector? Well, we'll take our magnitude, which is 3, times a cosine of theta. And theta is at 0 degrees right there. 3 cosine of 0 is simply 3, right? Because a cosine of 0 degrees is going to be 1. So 1 times 3 is 3. And again, if we think about vector b, what does vector b look like? Vector b is right here. It's due east. It's entirely in the horizontal. So the whole magnitude is all in the x direction, so that makes sense. Which means we should probably expect the y direction to be what? Well, if you have the magnitude of 3 times the sine of 0 degrees, because remember theta is our 0 right here, sine of 0 is going to be 0. So 0 times anything is going to be 0. So we've got vector A is a vector that's got its entire magnitude in the vertical, right here, and vector B has got its entire magnitude in the horizontal, right there. So we add them both up. But we're not going to add them up quite just yet because we still have vector C. Okay, so vector C, I'm going to write right there. What's the magnitude of it? It is 4 meters, or 4 paces. And this is not entirely in the x or not entirely in the y. It's both because it's at an angle of 45 degrees south of west. Okay, and so I'm going to draw a little arrow right there that reminds me what direction that's going in. And look carefully at that for a second. That means that the x component is going to be negative x, and the y component is going to be negative y. So we're going to need to put our signs in here to reflect that. All right, well, let's find out what the x component is to begin with. All right, for the x component, The magnitude is 4. Cosine of theta. Theta is what? 45 degrees. I'll put a little degree sign right there. Okay. So what is 4 cosine 45? 4 times cosine of 45 degrees. I get 2.83. 2.83 meters. And how about the magnitude times the sine of theta, the y component? Magnitude is 4, sine of theta. Theta is still 45 degrees, right? So 4 sine 45 gives me the same thing, right? Because a 45-degree angle has equal legs of a triangle. So 2.83 meters is going to be the y component as well. But one thing we need to do is we need to go back and look at what is the direction that this is going. Well, it's going in the negative x and the negative y. So that means we need to be very careful to make sure we put a negative sign in front of the x and a negative sign in front of the y, because it's got a negative x component and a negative y component. So what we've really done is broken all three of these vectors into their respective components. A has no x component, it's all y. B is all x and no y. And C has a negative x and a negative y component right there. So what we can do now is, since we broke them all into sort of like components, we can simply add them up. All right? So we're going to find out what the components of vector D are, D being the resultant of A, B, and C. And we're going to add them all up together. So let's add up all the x column. Well, we've got 3 plus negative 2.83, right? What does that wind us up with? That winds us up with 0.17, the positive 0.17 for the x component of D. Okay? How about for the y component? Well, we've got a positive 5 and a negative 2.83. Let's just subtract that 2.83 from 5. I get 2.17. All right, so that's 2.17. So it turns out that vector D has got a positive x component and a positive y component, but the positive x component isn't very big. All right, so this is the x component for vector D and the y component for vector D, but we want to know what the actual magnitude of vector D is. How do we get the magnitude? How do we get the magnitude of vector D? How do we get the magnitude of any vector if we know the components? We take the Pythagorean theorem. All right, but that means to get D itself, we're going to need to take the square root of those two components squared to get that magnitude. So if you recall, it's the x component squared, so 0.17 squared plus 2.17 squared, and that's going to give us our magnitude for D. So 0.17 squared plus 2.17 squared. I'm going to take that to the half power. So, well, it's going to be 2.18. 18 is a teeny tiny x component. It's mostly y right here, but the hypotenuse is going to be slightly longer than the long side. It's going to be 2.18 meters in magnitude. So that's going to be our magnitude for vector D, 0.18 meters. Okay, what direction is going to be in? What is the angle that it's going to be at? Well, we know to find theta that we take the inverse tangent, right? The inverse tangent, or tan to the negative 1, so that's going to be function and then your tangent button, right? Inverse tangent of what over what? Well, we know that tangent is opposite over adjacent, and so whenever we have any angle based off the horizontal, the opposite side is going to be the y component, or the y component, and the adjacent side is going to be the x. So for our purposes, it's always going to be the y over the x. So what's the y component of vector D? 2.17, right? What's going to be the x component for vector D? 0.17. Now I'm running out of room. Hopefully you still have a little bit more room right here. But let's find out what angle that creates if we take the inverse tangent of that fraction right there. So inverse tangent of 2.17 over 0.17. I got theta equals 89.6 degrees. It's a pretty high angle right there, all right? So I'm going to kind of dotted line box that. And I should dotted line box this too, because that's kind of part of our answer right there. All right, so our angle is not quite 90, although normally I would probably round it up to 90. 89.6 degrees The only thing we have yet to do is determine which quadrant is it in. Is it north of east, south of east, north of west, south of west? Well, look at what our components are right here. We've got a positive x, and we've got a positive y. So it's going to be kind of like that. Positive x and a positive y. What quadrant would that be in? Or what would we call that quadrant that it's in right there? We would say that's north of east, right? North of east. And oops, I'm trying to write with my laser. N-O-E. Or you could say it is above the positive x-axis. That's our other way of saying it. Okay? So let's just put it all together and get a statement for vector D. I'm going to write it at the top right here because I ran out of room at the bottom. So vector D, having added all the vector A, B, and C up, vector D can be summed up as being a magnitude of what? 2.18 meters. 2.18 meters, or paces if you wanted to use paces. At what angle? At 89.6 degrees north of east, or above the positive x-axis. That is our result, as our resultant vector D, which is the sum of A, B, and C added together. So that's how we add vectors together using the component method. And you can add them or even subtract them using the component method as well. But it may take maybe a little more time consuming at first. It may seem a little bit tedious because you got to watch your signs. All right, signs here, and you may have some negative, or you may have some zero components. But it's going to give you a very accurate answer. And so this is our component method of adding vectors together. So we're going to do some more in class, some more examples right here. But hopefully this makes some sense to you. And if it doesn't, please make sure you come see me, and I'll be glad to talk you through it. All right? Thanks for following along. I'll see you on the next one.